Okay, so what is the second derivative? Well, it's important to know this for a number of reasons. We're going to look at how firstly in this video. What is the second derivative? Well, let's find for y equals 2x cubed minus 3x squared plus 2x, this polynomial here. What's the derivative? Okay, and I'm going to call it the first derivative because we're starting with this function and we're taking the derivative once. And well, we know how to do this, okay? And using our formula for each of the power terms there as part of the polynomial, we would get 6x squared minus 6x plus 2. Okay, what if we took the derivative of this? Well, we'd sort of have to say, okay, now y is now not what it was. Y is now 6x squared minus 6x plus 2. So taking the derivative of that result from the first derivative, well, then we do the same thing. Each of these power terms, same thing, reduce the power by 1 and multiply the whole power onto the front with any of the other coefficients. And you would see that we would get 12x take 6, but we've got a problem because of the notation. This is saying dy dx is this is saying no, dy dx is that. So we need to sort out the notation and formalize this a bit. What we'd say is that 12x take 6 is the derivative of the derivative. So we took the derivative first time through and then we took the derivative of that and we got 12x minus 6. This is actually called the second derivative of y, with y being defined up there. But this notation is an issue because we've got two different things with the same name or the same designation. That's no good. So let's do this properly. We would say if y equals 2x cubed take 3x squared plus 2x, dy dx is 6x squared take 6x plus 2. Now if we take the derivative of that, the next stage would be written as the derivative of something you might know is with regards to x can be written as d dx of the thing we're trying to find the derivative of. So I'm going to leave a gap there, and what we're doing is finding d dx of 6x squared takes 6x plus 2, which we know how to do. We did just before. Okay, that's going to be 12x take 6. What do we write on the right side? Well, the thing we've got on the previous line is dy dx. See straight above? Now we use what's called a bit of pseudo algebra. We've got d and d is d squared. It's not purely algebra, but the notation works in a pseudo algebra style. And we've got dx dx. Okay, now it's dx all squared. Now where the notation doesn't align itself with regular algebra, we don't put brackets around this here, okay? But it means dx squared. So do not write these little brackets here. I'm just indicating where I'm talking about. That's what it means. So that means the second derivative, that notation, the second derivative of y with regard to x. The second derivative of y with regard to x. Okay, so the process is really just find the derivative, then find the derivative again, and you've got the second derivative. It's interesting to note coming down here the nature of the functions you get as you go from y to the first derivative to the second derivative. And there are higher order derivatives as well. So we could go beyond that. What would that look like? Well, we would have, if we call that d squared y dx squared, the second derivative, we'd have d cubed y dx cubed would be the derivative of that up there, which would just be 12. It's a constant term. And we could keep going. The fourth derivative, fourth derivative pretty rarely used, and that would be 0. And in fact, if we kept going, what would be the answer to all of the derivatives beyond that for this particular function? It would be 0 again. So the rate of change of 0 is 0. It's a constant. Okay, so let's have a look at the graphs of that. And we've got the first function, 2x cubed minus 3x plus, 2x cubed minus 3x squared in the red there. And we got the first derivative of that, which we found out just before. Okay, and it was a quadratic function. It was back on this page here. We saw that that was 6x squared takes 6x plus 2. Okay, and then the third one is a straight line. And then the fourth one and thereafter are just constants. Okay, so that's how it rocks. So it's an interesting little phenomenon if you graph it. There's some other sorts of notation there. Sometimes that one, or when you start to get to a silly number of dashes there, you might even see little 3 there, for the third derivative. Okay, there's many different types of notation. There's a different one there. The function notation and the dny dx to the n, where n is the order of the derivative, is those two there. This one and the function notations above, they're the common ones. Okay. Well, it says find the second derivative of each. I've only got one. Okay. So we've got the product rule. So dy. I'm going to use the Leibniz notation, and we've got the product rule there. Okay. So the first derivative is e to the x sine x plus e to the x cos x. And then we've got the same thing for the second derivative, the same process, but we've got two lots of the product rule. So we've got, okay, so we've got the first part in yellow there. The product rule has been applied to that. So you can see it's just a repeat of what we had in the beginning for y. And now for the part here in light blue, all right, we're going to do that in that space right there. And that's e to the x cos x. So the product rule applied again, derivative of the first times the second plus derivative of the second times the first. And then we've got, we can remove the brackets at this point. We've got like terms in a sense that we've got, we can algebraically add some of these things. Now we've got e to the x cos x plus another e to the x cos x. That'll be 2 of those. And then we've got e to the x sine x, and then e to the x sine x, but it's negative, and they will cancel out, you see. So we have 2, it's the purple stuff, right? 2 e to the x cos x is our answer. Last bit now, if we have f of x equals e to the 2x, find f double dash of x, f double dash of 0, I should say. And what that means is that find the second derivative and then sub in 0. Okay, and we'll get a definite answer there. So one way I could do is just do bits at a time. The first derivative, f dash of x, that's just a chain rule. So it's 2e, so the derivative of the inner function is 2e to the 2x. Okay, now the second derivative is the derivative of that, and that's another 2 times 2e to the 2x. Okay, which is 4e to the 2x. Now, f double dash of 0 is when we sub 0 in, it's function notation after all. And we have 4e to the 2 times 0 is 0, e to the 0 is 1, 4 times 1 is 4.